All right, so let's pick up where we left off, which was just introducing the idea of strings, right? And so strings are an object, so they are, variables that point to strings or do so by reference, right? It's a reference type. It's not a value type. It's not an array of characters. We're going to look at arrays today as well. But strings, while it represent a sequence of character values, are not arrays in of themselves. So if you come from a different programming language background in which strings are arrays of characters, it's not the case here. Now, I'm going to go relatively quickly here because a lot of this you can probably familiarize yourself just by reading about Java strings. And it's not much different than any other programming language. And you've dealt with strings in some programming language, I'm sure. There's obviously a way to create them. Usually we do so with the literal double quotes. One thing to know is that while most Java objects are created using something called the new operator, which we'll see a little bit later today with arrays, strings can be made with the new operator. And as such, they are like other objects in that they can be created with this special keyword new. And we'll look at exactly what new does in a day or two. But generally, we never need to, because strings we can just literally write whatever the string is, right? And so usually we don't ever really use a new operator. We create strings literally, and then we create new strings by combining existing strings, which brings up the point of the idea of strings being immutable. Before we go into that, here are some string methods. This is now, string is an object, has instance methods. We haven't really learned how to write instance methods or design objects, but again, that's not really the point of this class, and we just going to touch on that a little bit before we dive into data structures. But the idea here is that a instance of a string has methods that you can call on that string. This is the difference between static methods, which are class methods, which exist as soon as your program begins and can be referred to through the class name, and a instance method is that in an instance method, we need an object in order to operate on. We're asking for the instance method of a particular object. So we have an object reference, and then the dot operator, and then the method of the name of the method, the instance method we're trying to invoke. String, like other objects, has useful string methods, and in particular, make note of equals. So you never should compare two strings with the double equals operator. And the reason why is because the double equals operator in Java, for comparing the equality of two things, when it is used with a reference type, like, for example, string, what that double equals operator is testing is whether or not two strings are the exact same spot in memory, whether or not they are, in fact, the exact same object. Now, this is different than some higher order understanding of what it means for two strings to be equal. When we say two strings are equal, we usually mean this higher idea of, well, relative to the string, like, they have the same characters in the same positions, and they have the same length, right? That is a notion of equality that has to do with the semantics of what it means to be a string, right? Now, that is not the same as they are the same object in memory. We could have two different string objects in memory in two different places, which happen to be the same characters in the same sequence and the same length. These two strings, with respect to the idea of being a string, are in fact equal. So you should always use, the upshot of this is you should always use the equals method of one string in order to, and pass, we're not showing the parameters here to these methods. Equals takes a reference to a different string as its parameter, and you'll get back true or false whether those two strings are equal with respect to this character by character thing. And that is why we don't use double equals as a way of testing the equality of one string to another, right? All right. Toward that end, and this is more about this notion that strings are immutable. Once you create a string object, it's never going to change. I really want to get on to the rest of today's lecture, and so I think we're just going to skip these notes. And if you read these notes, and if you have any questions, come armed next time you see me or in office hours. Right? All right. And there's two code examples in the lecture example code that you can play around with that demonstrate the notes on that. Right? What I'd like to do what I'm trying to get to this lecture and really like to spend some time on is this idea of of having a mental model for how a Java program is running on a mental model of computation for how a Java program runs, right? And this is essentially an environment diagram is another way of thinking about this. And it's a way to visualize the two areas of memory that a program uses, the stack and the heap. Now, all of you just came out of 110 for the most part, and I know that Chris Jordan does a great job of explaining the stack and the heap and how to write and work with an environment diagram. But I guess what I'm asking is that true? Like, everyone raise your hand if that statement is true. All right, good. Okay, so for many of you, you'll understand what I'm talking about, and therefore I can hopefully most of this is just review. Right? If you've never seen an environment diagram before, it's not terribly difficult. You just have to understand what happens when one method calls another method. So basically, the way this environment diagram works, and you're all familiar with it, we have the stack, and that is keeping track of our call frames, which on our stack of call frames, we have a call frame for every method call. That's why we call it a call frame. And we start off a program with one call frame on our stack, and that's the main call frame, right? Because we start off in the main method. In a call frame, we keep track of all the local variables that are part of that invocation to that method. And this includes the parameter values, right? And basically what happens is that we have we execute our program, and wherever we use or need local variables, we're going to get that in from the call frame, which maintains essentially a table of local variables and their values. Now, the value types, which are represented just by a value, right, not an object in memory, that value is in the call frame just as part of that table, right? The reference types, that's basically anything that's an object. What's in the call frame as the value of the local variable is really a pointer, a memory address into memory where the object actually lives. That piece of memory where objects live, we call the heap, right? All right? And so, so when a method is called, so like I'm in main, and I'm going along, and I'm executing instructions, and as those instructions work with and update and otherwise declare local variables, that's changing that table on my call frame, right? Every now and then, it might actually, if one of those variables points to an object, and I work with that object, I go through the reference of that value in my call frame in order to find that object in memory, and then I can poke around and get to fields and methods and data associated with the object, right? And we'll see this in a bit, right? At some point, if this method calls another method, what happens is we create a new call frame for the method we're about to call and push it onto the stack. So I'm going to show stacks growing from top down, but sometimes, often they are visualized as growing from the bottom up. It doesn't really matter whether they go from top down or bottom up. The idea is that this new call frame represents this method I'm about to call. Right? And so we set up that piece of memory, and we make it, and then we create its table of local variables, including the parameter names and the values I'm providing when I make the call. So I get a new call frame for every invocation of a method. Even if the method calls itself, and you'll see this on Thursday, right? Even if it's recursive, every time I call a method, I get a new call frame, and that call frame is where I keep track of my local variables, right? Then when a method is done and it's about to return, its call frame is typically removed, right? And we go back to where we came from, now with the value that's being returned by the method, and so then we keep going, right? So we can visualize this, right? What I'm going to do is I'm going to leave presenter mode because I'm going to go back and forth between looking at a slide and looking at code. So I'm just going to do this to make the slide as big as I can without. Where's the bar? There's a bar somewhere here that lets me just change the size of this, is there not? There it is. Right. And right. Okay, so let's go to, if we go to lecture 3, example 4, we'll see a relatively straightforward little program, right? We start off in main, and our first line of code is this line 6, and we can, now we can, we'll look at exactly the syntax for arrays a little later in this lecture. But if we look at this line, what it's doing is it's declaring a local variable names, right, which is going to be a reference to an array of strings. And that array of strings has 3 elements. The first is the string Joe, the second is the string Bob, and the third is the string Bill. So after this line 6, right, what our stack and heap look like is something like this, right? So what happened is that, well, we started with a call frame for main, because that's where we always start. And we have args as a parameter. And so presumably args as a parameter is a pointer to an array of strings. And so it is, right, a pointer array of strings. We never use args. We're not giving it any command line arguments. So this array is basically 0 length. There's nothing there. But I'm just putting it here for completeness. When the main program started, that's what our call frame looked like, right? It had args defined as a reference to some place in memory, which was an array of strings, because arrays are reference types. They are objects. And at that place in memory was the data that is being stored as part of an array. And here I'm visualizing the length field of an array being set to 0. And it doesn't have any elements because it's an empty array. Right? Now, at line 6, we declare this name names, right? And that is when it gets added to our table. So now we have names, and its value is, is whatever is on the right-hand side, because we are assigning the value as well. The value is a reference to this array of 3 strings. So that's going to be somewhere in memory. That's going to be created in memory. Here, I've listed it as being created at address hex 23A. Where do these addresses come from? I'm just making them up, right? I mean, obviously, when your program really runs, the addresses come from somewhere. They come from the operating system and the underlying Java virtual machine that's running your Java program. But for the purposes of an environment diagram, the actual number doesn't really matter. I'm just making it up. So here we're pointing to this array at, let's say, hex 23A. And it has a length field of 3, because that's how long this array is. But it also has, right, data in there. It has a 0 element, a 1 element, and a 2 element. And those elements are strings. Now, string is not a value type, right? If it was integers, then we would just see their values right there as part of the data of the object, right? If they were just Booleans, we would just see the value true or false right there inside the object, because value types are represented by a fixed size value, right, of like a bit pattern, and so aren't objects in memory. These are reference types. These are 3, this is an array of 3 strings, and therefore the value of each element is a reference. So the 0th element of this array is a reference to this string, which is stored at memory hex AB1, right? And so on and so forth. All right. So that is, before I go any further, I want to make sure that hopefully everyone, this was a refresher for the idea of environment diagrams. Any questions about how we got to this point and this state of the world? Yes?
Can you just reiterate what you just said about value types, where they're actually...
Sure, right. So if I wanted to, in my, here. If I was trying to represent on my environment diagram an array of integers, right? Let's say that was supposed to be like this, right? Let's say this is going to be some other array, and it's an array not of strings but of integers. Then I would put the integers value right here, right? In other words, let's say this array's values were 56, 21, and 8, right? So in other words, these values here wouldn't be pointing to something else in memory, that's a separate object or a separate structure. It would just literally be the value right there. Does that make sense? right? and the idea here is that's the difference between a value type and a reference type. A value type, the data is just there, right? That is the value. Whereas a reference type, it's represents the actual value you store in order to refer to this to that object is an address, which then tells you where to go.
When you say there, you mean like stack? That's where the
Wherever you end up with the reference type. Sometimes it's on the stack because names is a string. I mean a reference to an array, right? And therefore we have an address, and then we expect some object here to match that address. But here again, like this is not on the stack, but is a reference type as that's part of the data within this object, and it is referring to some other object, right? A string is a string. Okay, so right, I made a couple of, when we started, I said something about strings being immutable, right? Where like a string object. So I'm talking about like Joe, Bob, Bill. Objects in memory that represent strings are in fact immutable, right? They are that sequence of characters, and that's and they are never any other sequence of characters. And so, but a string array or any other kind of array, right? That is mutable. In other words, the array, while the length of the array can't change, each of the elements in the array could change, right? And so I could go through this reference names, get to the 0th index, and I could assign into that 0th index a different reference and change which string it points to, right? All right. Okay, so let's keep going in our program and kind of trace what's going to happen. Now at line 8, right, we have a new name declaration, longest, and it's being initialized to a value 0. So what happens when we do this? Whenever we encounter a declaration of a local variable, it gets added to our table in the call frame, right? So here is a local variable that's being declared longest. And so now we have a new entry in our table longest, and it gets a value. And in this case, it's an integer, so its value is just whatever its value is. In this case, it's 0. And so after line 8, we end up with a new variable or name in our call frame and a new value that goes along with it. So now let's kind of step down to line 10 and 11, right? So we get to line 10, and we end up in a for loop, right? So the first thing that happens in the for loop is a declaration of a looping counter that gets initialized to 1. Now remember, a variable that's, I mentioned this when we talked about for loops, a variable that's declared inside a for loop, either as part of the declaration of the looping variable, right, or even inside the body of the loop, right, a local variable is scoped, is valid in the tightest enclosing block of statements, which means that this I is not valid in the entire method, right? It's only valid inside the for loop, right? And so what we'll see in this example as we keep going is this I will appear on our call frame when we declare it, when we enter the for loop, but then when we exit the for loop, it'll get thrown away. It'll get taken off of our call frame when it goes out of scope. And that's how variables can come in and out of scope. Most local variables inside a method are not inside some looping block or not inside some clause or whatever, so they're just in scope for the whole method. But that explains how variables go in and out of scope, is that they get added to the call frame when their declaration is encountered, and they get removed from the call frame if they fall out, if the execution leaves the block where it got added. Right? So here we're going to add I to our call frame and set it to be 1. Right? And we're going to then, okay, so now we're at 1. Now we're about to call is longer. Okay? And so so now we have so now we're going to make a method call. The first thing we have to do before we make the method call is to resolve these two expressions, right? We're asking for the ith value of names, and we know I is 1. This is the first time inside the loop. And we're asking for the longest value of names, right? So, and we know that that was set to 0 up here, right? And so, to resolve the ith value of names, we go through our names, right? So names is the variable name. It is a reference to an array, which we then index to the ith value. I comes from our call frame, that's 1. And so names of I is going to be hex 235. And hex 235 becomes the value, right, the reference that gets passed to this isLonger method, helper method, as the reference to string A. Right? And so that's how, when the isLonger call frame gets created, the value A gets the value hex 235. Similarly, right, the second argument we provided isLonger when we called isLonger was the longest index within names. The value of longest comes from our call frame, 0, and the value of names, of course, also comes from our call frame. We follow names, right, and then go into its 0th element, and that picks out that reference hex AB1, right, which then is mapped to the value of the parameter B in isLonger in its call frame as hex AB1, right? So that's how we're able to use our call frame, right? The main's call frame, I'm talking about our as if we're main, how we're able to use the call frame in main in order to resolve any of those values that we needed, names, I, longer, right? In order to evaluate those expressions, in order to then have values, or references, in this case, reference values, that get mapped to the parameters that of the method we're about to call. Now we're in isLonger, right? We pick up execution here using this new call frame as our environment for how we resolve names. All right, so any questions at that point? Just want to make sure we give everyone a few seconds to digest that, think about it. Okay. Okay, so right. Okay, so I'm no longer going to draw the arrows everywhere because otherwise it's going to be really, really confusing because there'll be arrows all over the place. So instead, I'm taking the arrows out, but if you ever need to see which object this is, just look for the matching address, right? So objects are labeled by their address. Okay, so now let's go to line, so now we're inside isLonger, and, we keep going, right? So we end up with a integer a length, which is, set to the result, whatever we get back from calling the length method of a. I'm not tracing down into that, but we'll get back some value, and that value will be set to the a length and the b length, right? So now we have, as we encounter these declarations and their initial values, we set up our call frame accordingly. And then now we're at the very end where we're basically saying, okay, we're going to compare a length to b length, and if a is greater than b, we return true, and if a is not greater than b, then we return false, right? Because we're trying to see if a is longer than b. And so, right. So 3 is not greater than 3, and so the return value here is going to be false, right? So now we know what the return value for this call to isLonger is. Now we can get rid of the, we throw away this call frame and go back to main and go back to where we came from, which is right here, right? And so now that expression is false, so we don't update longest, we just skip over that, and then we come back to the for loop. I, right, which is in our call frame, gets incremented from 1 to 2. And now we're right back into line 11 the second time. So the second time, right, Now we get a different call frame, right? There's not just one is longer call frame. There's an is longer call frame for every call that gets made. So it's created when the call gets made, it's used while the method is executing, and then when the method returns, that call frame is thrown away. And so then when you call it again, we create a whole new call frame and put it on the stack for this subsequent call to the same method. This is why recursion can work, right? Because every call has its own call frame with its own copy of the local variables. And so you can have a method that calls itself, that calls itself, that calls itself, etc. And on Thursday, my guest lecture will demonstrate a trace through a stack heap example using recursion. All right. Okay. So the second time through, we get different values for A and B, right? Because the second time through, I is now not 1, it's 2. And therefore, we resolve the A, that first parameter is 2C1, right, as it gets passed to is longer. The second call to is longer. Longest remains 0, and so that second parameter remains the same, right? Just by happenstance, the second time we called is longer, that second parameter was the same string as it was the first time, right? Now, and then we can execute through is longer, right? Getting the A length and the B length, and this time A is greater than B, and so we're returning true. That takes us back here, where now we're true. So then we go into the block of statements that we execute when an if statement is true, and this updates longest to be the value of I, which is 2. And at that point, right, we get through the for loop, and we're done with the for loop. I is now 3, and that's too long. That's too many. It's greater than the length of the array, or is the length of the array. And so we exit the for loop. When we exit the for loop, the integer I has fallen out of scope, right? It was declared inside the for loop. Now we're outside the for loop, and so that variable gets taken off the call length, right? But that's okay, because we don't need I anymore. I has served its purpose, right? Now we're left with our answer sitting in longest, which got updated from 0 to 2 that second time through the for loop. And so when we print our answer, we know which index to go to in order to print the name that we care about. All right. So that idea of being able to keep a mental model of a Java program running in this stack heap kind of manner, that's really useful for visualizing what your programs are doing, or where we might have bugs, or just understanding how code works, right? All right. So we've seen arrays a little bit, right? But we haven't really gone through the details. So here I'm just going to go through some notes on arrays. You should have seen some form of array in some prior programming language context. So most of this should be relatively familiar. There are a couple of things about Java arrays which are unique, one of which we've already said, or I've already mentioned, which is once you create an array of a certain size, it can't change in size. Now we're going to encounter a different kind of data structure called a list, and once we get to the data structure, it's kind of part of the course starting next week. It'll be we'll be very concerned with this more general abstract notion of a list as a sequence of elements, right? But an array is a specific type of thing. It is a contiguous set of memory, which is all the elements that's required for the array. And because you have to allocate an array, you need to know what in Java you need to know how long it's going to be, so that you can so it knows how much memory to give. So once you create an array, you have that much space in the array. Whether you use it or not, or how you use it, is up to you. u, of course, and then but it can't grow any bigger, and it can't get any smaller either. It's not like, even if you're using the array in a way that you're only using some number of the elements at the beginning, and we'll do this very thing when we implement the list data structure. It doesn't, that's, the array itself, right, is what it is, right? That's on you to keep track if that's how you're going to use an array, right? So an array is a certain number of elements of a specific type. And that's the other thing about Java arrays, is that you have to type them, just like anything else in Java. So you can't have an array where the first element is a 0, and it's an integer, and the second element is a reference to a string, and the third element is a real number. That's not allowed, right? An array as a structure is a sequence of elements that are of the same type, right, strictly, right? That doesn't grow, doesn't shrink, and is always just what it is. Okay, so here's some syntax for how you declare an array and to create an array. Arrays as a type declaration are a little unique. There is a class called array with a capital A, but that's not how we specify an array type, right? So, like unlike strings where there's a string class and it's capital S string, and that's the same as the type name that we use when we want to refer to a string. For an array, we're combining the idea of an array with a specific element type, right? So we need to have an array of something. And so the way we specify that, the type specifier for an array, is to take the type of what's in the array, the element type, and then put square brackets at the end to indicate we really mean the type of an array of these things, right? So a string with square brackets after it isn't one string. It is an array of strings, right? And we can do that with any type. We can even do that with arrays. We can say that we want an array of arrays, right? And that's how we do multidimensional arrays. So, so that's the syntax. And the syntax, and then to create the array, so that creates the, that's the syntax for the type declaration for any names that we want to be able to refer to an array. But then we actually need to be able to create an array. So how to create an array is the use of the new operator. We say new, and then it's the array type specifier again, but now with a value in the square brackets providing the length of the array that you want. Once you've created that array, right, that expression, new, and in this case, string array of size 3, right, once that is an expression that evaluates to the reference to the new array that was just created. So, and that is what we are storing in the name itself, right? And then, just creating the array doesn't create or set the elements inside it. In other words, I have an array of 3 strings, but that means that each element at the very beginning is set to this special value null that we'll see in a bit, because I haven't actually set any of the elements. So after you create an array, you need to then fill the array with the values you intend to have inside the array. So in this case, these 3 strings that I am now setting to, I'm setting these specific elements to these specific strings. There is a way to specify an array literally so that you can declare an array and set it to an array of specific, specific values that you provide literally at the very beginning. So you can do all of that in one go if you want. The syntax, I'm not going to go over the syntax in detail. It's on this slide, and you can play with it in Eclipse if you want. So there is a way to specify an array literally if you know the values that you're going to put in all the different element positions. Once I have a reference to an array, I need to be able to work with its individual elements, like extract the values and set the values. And so that's, we need, in order to do that, we index into the array, either as the left-hand side of an assignment operator in order to set an element value, or as part of an expression in order to retrieve the value, right? It's zero-based indexing, which means the first element in the array is 0. The last element is length minus 1. So length of the array as an index is illegal. To get the length of an array, you use the length field of the array. So this is a little different than string. For arrays, if you want to know how long they are, you just need the array reference, and then you can say dot length, and that will access the field. That field cannot be changed and is immutable. It doesn't change. The field it is, right? The array, obviously, we can change. We can change the elements. But the field is the length because the length of the array is set and doesn't grow or shrink. And so you could just use that value and know that that is the length of that array. Now, note, that's different than when we ask a string for its length. String, the length of a string is found out by asking the string to execute an instance method that calculates its length and returns its value. And the reason why is because there can be strings that have escape sequences, and otherwise it may not be completely clear exactly what the length of the string is, and so the string might need to do some work in order to understand exactly how long it is relative to the characters being used. Whereas in the array, it's set and known in advance, and so it's just a field. So there's an example in the lecture 4 code that just plays around with some arrays and demonstrates some of this. I'm going to leave that for you guys to explore on your own. I did mention this special value null. So because when we declare a reference type, or a name that can point to a reference type, until we assign it, it doesn't have a value. Just like when we create an array of strings, until we actually assign the elements, those elements don't actually have a value. So there's lots of places where we may need or expect to have a reference to an object as the value of some name, because it's a reference type. But for one reason or the other, there is no object. We don't refer to anything. So we need a special value that can be used with reference types that essentially means I have no value. And that special value in Java is null as a keyword, right? So the literal null. And so anything that is null, any reference type that is null, is basically trying to indicate that value of null, right, is a special null reference that essentially means no reference at all. It's either a name that was created, or an element in an array that was never initialized, or a name that was never initialized, or sometimes it gets used as a way to signal that something's gone wrong or that something doesn't exist, right? And so the value null, you are free to use it as a value that you can use in any situation where you need a reference value, right? It is a valid value, but if you ever take anything that has the value null and you try to do anything with it, so if you have a null pointer to a string that is null, or you have an array that is null, and you try to take that string and you ask it for its length, right? That is going to crash your program. That is a runtime exception. It is a null pointer exception. So even though the value null can be used as the value for any reference type, it is a valid value. It can be tested. I can ask if a particular reference is null by saying double equals null, right? And I can set it. I can take a name and set it to null if that's somehow part of what I want or want to do. But I have to be careful, because if I have a reference that is null and I ever try to use it in any way, shape, or form, right, it will crash your program as a null pointer exception. Which means that if you have generally when you are programming and you are programming a method that accepts some parameter, which is a reference type. So like, let's say a method that accepts as its first parameter a string, and the second parameter an array of something. Before in your method you can use those values, you should check to see if they're null. If they're null, that probably means whoever called that method didn't do something correctly, right? And so, or it could be that whatever method you're writing has some, valid or appropriate response for what the value should be, or what you're going to do when you're given a null reference. But the idea here is that if that's the case, you need to test for that null before you ever try to use it, because otherwise, if somebody gives you a null reference, then you'll end up with a null pointer exception. All right. One important point here is that arrays as reference types, because they're reference types, if you have a name that refers to an array and you have another name that refers to the same array, right? They point to the same place in memory, then those two things are the same array. Same reference, same array. And so even though you might have that reference in two different names, that doesn't mean you have two different arrays. It means you have two different ways of getting to the same array, right? So this has some implications for when you pass arrays to other methods. If you pass an array to another method and you don't, it's not a copy of the array that you're passing. You're passing the actual reference. So now that method has a reference to the array that you passed. And so if that method then goes and changes things, right, goes in, changes the elements of that array, that is changing, when that method is done, those changes are permanent. Those changes are have been made to that object, and now the array that you started with is not the array that is not the same as, after you call that method than before you call that method. So if you're in a situation where you have an array and you do not want the array's elements to change in any way, but you need to take this array and pass it to a method, but you do not know what that method is going to do with your array, or maybe you do know what it's going to do, and what it's going to do is going to change the elements, but that's not what you want to happen. You want to pass, if you pass your array without copying it, it will, you'll be giving away your reference to the array, and that method can do whatever it wants, and those changes will be made to the array that you passed. So if you need to pass an array, and you need to guarantee that your array does not get changed by the method that you're passing it to, even if you don't know what the method is going to do, then you need to make a copy of your array before you pass it. And that is easy to do. Every array has a clone method, and the result of the clone method is a new array with the same type and the same number of elements, and every element copied from beginning to end. Right? So example 2 in the lecture code shows this, but I want to go ahead and go to example 3, where we're going to trace through a small program that uses arrays and passes that array to another method that then makes a permanent change to kind of see this in action. So we go to example 3 in lecture 4. We'll see this example here. So we start off with a declaration of this integer array, right? And right, so we start off in main, and of course, that means that we have some value for args, and I'm just putting it here just to be complete. We don't really care about it because we're not really using it. But now we're here at line 7, and we've declared this name A, and this A is a local variable that is capable of referring to an integer array. But notice I've declared it without setting it, right? So we know what happens when we declare a variable. It gets added to our stack. But I didn't actually set it to anything, and so what's its value? Well, because it's a reference type, and I've declared this variable without having initialized it, then it automatically gets initialized to the special value null. So after line 7 here, we have null as the value of A. Now, of course, we get to line 9, where now we have an expression here which creates a new integer array with 3 elements, right? And so that means that we have a new object on our heap. Here's our length 3 element int array. And again, I didn't set any of the element values. So the element values get set to the default value for the type, which in this case, for integers, is 0. And so I have 3 elements, and they do have values. They just are all 0 because I didn't specify otherwise. If this had been an array of strings, and I didn't set the values of each element, then I would say that these would all 3 be null, right? But in this case, it's an array of integers, so the default value is 0. And then the next 3 lines, right, are going to set the values of each of those elements, right? We're going to go through A to the index and then set each element. And so those are the next 3 lines to set each element. Fine. All right. When we get to line 14, right, we have this line here, which declares a new name B, and that new name has the type integer array, so it can refer to an integer array. And in this case, I'm declaring it and setting its value at once. I've set it to the value of A. Now, that doesn't mean I made a copy of A. It means I set it to the value of A. And A is a reference to an array of integers. So B now is the same reference. So when I do something like this, right, I end up with a new name B on my call frame, and its value is the value of A, which A is a reference to this array. So now I have B that is a reference to the exact same array. So now I get to this point here, 16, where I declare a variable C, and I set it equal to the result of calling this method swap and sum. So I get a new new name C on my call frame, but I don't know its value yet. I need to go evaluate that right-hand side in order to decide what its value is. In order to evaluate the right-hand side, I need to call swap and sum. We know what happens when we call swap and sum. We create a new call frame. We add it to the stack. Swap and sum takes 3 parameters. The first parameter it's expecting is a reference to an integer array. And in this case, I'm going to give it the value of A as the reference. And then it requires 2 indices, I and j. In this case, I'm going to give it 0 and 1. So when calling swap and sum, we get a new call frame. And the A gets passed as the value of I array, and 0 and 1 gets passed as j. Now I'm inside this swap and sum. This is kind of a little silly. We basically take the ith thing that we found in I array and put it into a local variable called temp. We take the jth thing and put it into the ith spot, and we take temp and we put it into the j spot. That's the swap. And then we just take those 2 things and add them together, and that's what our return is. That's the sum, right? And so as we are going through that code, how it looks on the stack is, right, we declare temp and make it equal to I array, the ith value of I array. So we can go through I array to the 0th value, and there's our value 3. So that's how we get 3 for temp. Now we take the jth element and set it equal to the ith element. So that's going to copy from 1 to 0. And then we copy, then we set the 0th element to the value of temp. So temp's been holding on to 3 for us. And so now or the first element, the index 1 element to temp. And so that updates these 2 elements. And so we executed a swap of these 2 elements of the array. Then finally, we return 8, which is the sum of those 2 elements, and that's the value 8 that comes back to provide, to complete the evaluation of the expression in order to set C. Right? Similarly, if we did swap and sum with the B reference using 1 and 2 as the indices in order to get the value of this new local variable D, right? We now send the value of B to swap and sum. B and A are the same array. Therefore, we are calling swap and sum with the same array that we called for in the first place. Even though we use 2 different variables, same array, because they happen to point to the same array. So anytime you have a reference variable, right, 2 reference variables, right, if they happen to point to the same object, they are the same thing, and therefore, same reference, same thing. And so I can have multiple or different variable names that happen to point to the same thing. And so if I manipulate it through one name, then those changes are seen through the other name just as easily because you're working with the same exact object. So then we can, it goes through and basically does the same thing. Now swapping 3 into temp, and then swapping the 1 and the first and the index 1 and index 2, because in this call to swap and sum, I is 1 and j is 2. Calculating the return value of 13 and setting d to that return value, right? Now notice how things are different if I clone, A and set the value of the result of cloning A to B, right? So when I get to line 19, right, just before I execute 19, A and B happen to be the same array. But now I'm going to reset the value of B, right? I am going to replace this value of B with the results of this method of A, right? This is an instance method of an array. All arrays have a clone method. It's part of being an array, and you can, and if you ask an array to clone itself, it'll create a new array in memory, copy all of the elements, and then return a reference to that new array. So the result of this expression here is a reference to that new array, which we can see, illustrate like this, right? So before line 19, right? And now I ask this array A, through A, so this particular array to clone itself after line 19. I have a new array here, and I've updated B to point to this other array. So they start off the same, but now they're different arrays. The same in the sense that every element in every position is the same, but they're actually different arrays. So now if I work with A and change it, the array pointed by B is a different array entirely. It still retains its original values. And so we can see that in the next couple of lines where we, call swap and sum with B, but now that's this new second array, and we end up swapping and summing. And so we take C plus D, then we add A's length, then we set it to B sub 2. That's how we ended up with 24 there. And then, then there's some swap and sum through B, and then we update A0. So anyway, so these next two lines do a couple of different things and work with a couple of different objects, and you can kind of match those up with the slides in order to see what's going on. But the idea here is that if you need a new version of your array in order to give it away or pass it to some place where you don't know whether they're going to change it or not, and you need to make sure your array does not change, then you can do so using clone. All right. Multidimensional arrays are really just arrays of arrays, and as such, the different levels can be different sizes, right? So I actually don't like this about Java's array syntax, is when you do multidimensional arrays, you fill the dimensions from left to right. I actually think it makes more sense to fill them from right to left, but it happens to be that you fill from left to right. So here, marray is an array of integer arrays. And so when I create, this is how I create an array of 5 integer arrays. See, this doesn't make any sense to me. It should be here. The 5 should be there, damn it, because that is the type, integer array. But whatever. Anyway, so this is how so that first level array has 5 elements, each of which is supposed to point to a different array. And then in this little example here, I happen to make them all the same size, all those 5 that next level. So here I'm going through the first level to each of the first level of marray, which is an array of arrays, and setting each of these elements to a new array. And now if I wanted 3 dimensions, I would have an array of arrays, and then I go through those elements, setting them equal to array of arrays that I create, and then go through all of those elements in order to set them equal to arrays, right? So you have to go through all the dimensions and fill it out as you will. The nice thing is that it doesn't have to be regular. You can make different elements along a particular dimension, different sizes if you want, if that somehow is better for you or matches your needs better. But because regular arrays that have the same number of elements across both dimensions or 3 dimensions or all the dimensions in a regular pattern, because that is so common, there is a special syntax that will essentially do this work for you. But if you know the dimensions, all of the dimensions, you can specify them all at once in order to create your multidimensional array, and it'll create all the appropriate substructure all the way down to the end. Now, at the end, those elements will still have their default value. So here, I have a multidimensional array with an array of 5 arrays. Each of those is an array of 10 integers. But because I didn't provide any values or set any values, all of those integers the elements there are 0. If this was an array of, if this was a 2-dimensional array of strings, then they would create all of the right structure down to the very bottom element level, but those elements would all be set to null. So you'd still have to go through and fill it. There are some nice methods for manipulating and using arrays that are just convenient, right? So to do a binary search into an array, or to sort an array in place into other ways of manipulating arrays. Those are all in this arrays, and notice the S class, right? So array without the S, that's the abstract name of the class that represents all arrays of all types, right? Array with the S, that's a utility class that's just full of static methods that will operate on arrays in various ways. So you can reverse them, or extract out a subarray, or sort them, or do a binary search in them, et cetera, et cetera. Right, and that's just a good utility class to know about in case you need to manipulate arrays. Instead of writing your own version of a sorter or whatever, you can just use the one that you know is correct, that's already implemented in the arrays class. Now, having said that, we're going to use arrays a lot as kind of a fundamental part of the data structures that we build in the rest of this class. And so I may sometimes ask you to essentially write something that is already written in the arrays utility class. I obviously do not mean for you to just turn around and call the one that's in here, right? And I will try as much as I can in the homework assignments to instruct you as to when you can or cannot use utility class methods like arrays in order to manipulate the structures that we'll be working with. On Thursday, I'm not going to be here. I am flying out Wednesday night to a workshop in Denver. Right? Yeah, Denver. I'm excited. So I don't know if I'm coming back. But on Thursday, my LA is going to be. I may not be able to find the airport. My LA is going to be. One of my LAs is going to be giving a guest lecture. What he's going to do is he's going to go through a couple of stack heap examples. We're going to trace through a recursion and trace through a for loop and kind of see the relationship between an iterated a problem that is solved via iteration versus a problem that is solved versus recursion, and and just kind of how that works in memory. Right, and then on Tuesday we'll probably have one more lecture that's the same between us and Comp 401, where we talk about basic objects, just how to build a basic object, and that'll essentially be our first data structure. And then from that point, we'll go off to data structures, and so the two classes will diverge. Now, so all of this has been mostly just to get you up to speed